In this video, we're going to do example 1 from lesson 15. Question A says, verify that the given function satisfies the 3 hypotheses of Rolle's theorem, and then go ahead and find the numbers x equals c that satisfy the conclusions of Rolle's theorem. So first, and here's our function, and here's our domain. Remember, that's just saying pi over 8 is less than or equal to x, which is less than or equal to 3 pi over 8. And the first hypothesis of Rolle's theorem is that if a function is continuous on the closed interval. Okay, so my function f of x, which is sine 2x, that function is continuous on all real numbers. In particular, it's continuous on pi over 8 to 3 pi over 8. So it's fine to just say that, the graph of sine of 2x, sine is bounded between -1 and 1. There's some period stuff happening here, but there's no places when that's kind of a sloppy sine curve, but there's no places where you're having to pick up your pencil to draw a sine curve. So number 1 hypothesis is really just a matter of stating it. The second hypothesis is that the function is differentiable on the open interval, pi over 8 to 3 pi over 8. Well, in fact, this function is differentiable on all real numbers. The derivative of sine 2x, the derivative of sine is cosine of that stuff, chain rule, times the derivative of 2x, which is 2. F prime of x is 2 cosine 2x. That function exists everywhere. There's no domain restrictions. So it's fine to say that the function is differentiable on this interval. In particular, this is true since it's differentiable on all real numbers. As a general rule, we're kind of doing a proof here. As a general rule, we don't usually claim what we're about to show. Hey, I was able to take a derivative and there were no domain restrictions. But for the purpose of this video, I think this is the most straightforward way to do it. The third statement is that the function sends the endpoints to the exact same y value. Right? So here's your a and your b. So we need to show that f of pi over 8 is equal to f of 3 pi over 8. And we're going to do that right here. F of pi over 8 is the sine of 2 times pi over 8, which is the sine of pi over 4. Which is square root of 2 over 2, and f of 3 pi over 8 is the sine of 2 times pi over 8. Oops, 3 pi over 8. Which is the sine of 3 pi over 4, which is the 3 pi over 4. Here's pi over 4, 2/4 is pi halves, 3 pi over 4, we're in quadrant 2, sine is positive in quadrant 2. All students take calculus. Sine is positive in quadrant 2. So this is the same as the sine of pi over 4 which is root 2 over 2. The reference angle for 3 pi over 4 is pi over 4. Okay, so by 1, 2, and 3, those are the hypotheses of Rolle's theorem. We're now going to go find the x values, x equals c, that lie strictly between pi over 8 and 3 pi over 8, such that the derivative is 0 there. So by Rolle's theorem, one, 2, and 3 imply that there exists, you can do a little backwards E if you want, there exists an x value, x equals c, in this open interval such that the derivative there, let's even write it in blue, is 0. So there's some number strictly between pi over 8 and 3 pi over 8 such that the derivative of sine 2x is 0 there. Sine 2x must have some sort of horizontal tangent somewhere in that open interval. All right, we're just going to do a little bit of algebra to find the c that makes that true. Right? Of course, sine 2x, there's a lot of places, because it's periodic, right? There's a lot of places where the derivative is 0, but I want to find the specific one that lives strictly between pi over 8 and 3 pi over 8. Let's do that. We already found our derivative. It was 2 cosine 2x. You can just work with that, but let's go ahead and put c for a specific x value. Just put a c in there. We want to find that c that makes this equal to 0. All right? So 2 cosine of 2c is 0. That's what I'm solving. Dividing both sides by 2, we get the cosine of 2c is 0 divided by 2 is still 0. Take the inverse cosine of both sides. We get 2c is inverse cosine of 0. You can write arc cosine if you prefer. And of course, the cosine of what angle is 0, there are infinitely many number of angles that make that a true statement. Let's just look at a couple. Cosine is the x-coordinate on my unit circle. Here I'm up at pi halves, and my x-coordinate is 0, 0, 1. Also at 3 pi halves, my x-coordinate is 0. Or if you're more graphical and you just want to look at the graph of cosine, 1, 0, minus 1, 0, 1, there's just one period of cosine. This cosine is 0 at pi over 2 and 3 pi over 2. All right, I'm just going to leave the sketch of the unit circle one in here and not have the 2. So we get 2c is equal to pi halves, or 2c is equal to 3 pi halves. And really, if I'm being super tight, I want to add integer multiples of pi for this, because I can just keep whipping around the circle either way, and I'll have places where the cosine is 0. But I'm interested in the c value that lives strictly between pi over 8 and 3 pi over 8. On both of these, dividing both sides by 2, or multiplying both sides by a half, we get that c is pi over 4, or c is 3 pi over 4, and the c value that lives in between pi over 8 and 3 pi over 8 is pi over 4. Right? This one doesn't live in that interval. Pi over 4 is 2 pi over 8, and 2 pi over 8 lives between 1/8 of pi and 3/8 of pi. All right, so we verified 1, 2, 3 hypotheses of Rolle's theorem. The conclusion of Rolle's theorem is that there's got to be an x value in that open interval such that the derivative of 0 is there. We found the derivative, set it equal to 0, and solved for that x value that lives in that interval. We verified the conclusion. All right, now in part B, we're asked to find the average rate of change of f over the domain pi over 8 to 3 pi over 8. Remember that that is the slope, let's use a different color, slope of the secant line containing what points? Pi over 8, comma, go find f of pi over 8. We should write containing. I'm going to pause it and write containing, right? So it's just the slope of the secant line containing the points pi over 8, comma, go plug in to get y, and 3 pi over 8, comma, go plug in to get y. Right? And that slope is just f, change in y, all over change in x. And we found in part A that f of 3 pi over 8 was root 2 over root 2, and f of pi over 8 was also root 2 over 2. Three eighths minus 1/8 is 2/8, or a fourth. But we have a 0 in the numerator. This is 0. Answer, my average rate of change of f over this domain is 0. The slope of the secant line containing these points is 0. Which should make sense, right? Looking at Rolle's theorem, the slope of the secant line, because the function sends those endpoints to the exact same y value, the slope of the secant line for all of these is 0. Right? So now I want us to make a geometric connection, a visual, a graphical connection between the conclusions of Rolle's theorem and the average rate of change. And we've got an animation here to help us. All right? So here is my the function y equals sine 2x restricted to that domain. It's that part of the curve. And as you can see that function is nice and continuous on its domain, the closed interval, and it's differentiable on the open interval. I can't take the derivative at those endpoints. And if I move my slider along here, lo and behold, bloop, there is a place where the derivative is 0. There's a place where the slope of the tangent line is 0. We have a horizontal tangent there. And it looks like it's at about 0.786, that x value, and in fact that is pi over 4, the answer that we found in part A. So geometrically what's going on here is that there's going to be a place where the slope of the secant line is equal to the slope of the tangent line. These slopes are the same, those lines are parallel. And because with Rolle's theorem we're sending A and B to the same y value, the slope of that secant line is 0, which is why the conclusion, there'll be a place where the slope of the tangent line is 0 as well, follows. Let's summarize those findings in our packet, and that'll conclude example 1. All right, so we just got a little bit of a sketch. Here's my sine 2x on the domain pi over 8 to 3 pi over 8, and we sent both those x values to the same y value, root 2 over 2. My average rate of change, the slope of the secant line, is 0. And right here, the slope of my tangent line is also 0. And there's a place, x equals c, which we found to be as pi over 4, strictly between pi over 8 and 3 pi over 8, such that the instantaneous rate of change was equal to my average rate of change. Right? So at x equals that c ended up being pi over 4, the average rate of change and the instantaneous rate of change are both 0. Oh, I don't like the way I used the word at here. So at x equals pi over 4, the average rate of change and the instantaneous rate of change. Okay, I'm going to back it up a little bit, make it grammatically make more sense. The reason why I don't want to say at is because this average rate of change occurs over an entire interval, not at a particular place. So what I want to write is what we were saying earlier, is that there's a place in that domain at x equals pi over 4 where the instantaneous rate of change is equal to the average rate of change. And in this case, they're both 0. So I'm going to fix that real quick. All right? And they are equal, specifically they're both equal to 0. And that's because both these lines, they're not just parallel, both the lines are horizontal. These guys are parallel. In particular, they're both horizontal. All right, so that concludes example 1 with Rolle's theorem. Rolle's theorem is just a special case of the mean value theorem. If we turn Rolle's theorem on its side, if we turn this picture on its side, we will get the mean value theorem.